Hello everyone, my name is Nipun Musafta and today I will be presenting my research project titled AI-driven early suicide prediction from Facebook data. This project was undertaken as a part of my master's degree in advanced software engineering at University of Westminster. Right, so let's move to the problem background. Suicide rates are a significant global concern with thousands of lives lost each year. Early detection of suicidal tendencies can play a crucial role in saving lives. In today's digital age, social media platforms like Facebook provide a unique opportunity for this detection due to their widespread usage and the personal nature of the content shared. However, identifying relevant data amidst the noise and analyzing sentiment accurately is a challenge. My research focuses on leveraging this data for early suicide prediction using advanced techniques. Right, let's discuss about the identified gaps. Current research in this area has made strides but still has notable gaps. Existing models primarily focus on text classification but often lack the accuracy needs for reliable prediction. Most methods do not utilize advanced deep learning models like BERT, which can significantly improve accuracy. Additionally, there is a lack of comprehensive models that combine sentiment analysis with neural networks and is insufficient focus on real-time data processing. My literature review highlighted these gaps, emphasizing the needs for more robust and accurate models. Right, let's jump into the proposed solution. To address these gaps, I propose a BERT-based model for early suicide prediction using Facebook data. This solution leverages the power of advanced transformer models to enhance accuracy and incorporates real-time processing capabilities. The architecture diagram details the system's structure from data collection and preprocessing to sentiment analysis and suicide prediction. The key components of this system includes data collection and preprocessing, sentiment analysis using BERT, and a multimodal analysis approach for enhanced prediction accuracy. Right, welcome to the system architecture overview of our research project on suicide detection using a machine learning model. Our architecture is organized into three tiers: presentation, logic, and database tier. This design ensures a robust, scalable, and maintainable system. Let's explore each tier in detail. Each tier has specific responsibilities that together form the complete system for detecting suicide-related content in text data. The presentation tier is the user interface of our system. This is where users interact with the application. The front-end application sends the user input to the backend for processing and displays the result. We use the technologies like HTML, CSS, JavaScript, and especially the framework like Next.js. This tier ensures the user experience is smooth and accessible. The logic tier is the core of our system where the main processing happens. It consists of several components. The first component is data preprocessing. Here, the raw text data from the presentation tier is cleaned, tokenized, and transformed into a format suitable for model training and prediction. We use a level map to convert textual levels into numerical values and BERT tokenizer to encode the text. Then the next component is model training. This component involves training a BERT-based machine learning model on pre-processed data. The model is fine-tuned on a dataset of text entries with associated labels indicating the level of suicide risk. We use TensorFlow and Keras for building and training the model. The third model is model evaluation. After training, we evaluate the model using matrices such as accuracy, precision, and recall to ensure it performs well on unseen data. This component ensures model's reliability and generalization. Then the third model is real-time prediction. For real-time analysis, user inputs are processed in the same manner as the training data. The pre-processed text is fed into the trained model, which then predicts the level of suicide risk. The results are sent back to the presentation tier to be displayed on the user. The logic tier is implemented using Python and TensorFlow, and it runs on a AWS server to handle processing efficiency. Then the third tier is the database tier. The database tier is responsible for storing and managing all the data required by the system. It includes three components. The first component is training data storage. This is where we store the raw and pre-processed text data used for the training model. Then the second one is model storage. The trained model is stored in this tier. After training, the model is saved into disk using TensorFlow model saving functionality. This allows for easy loading and development of the model without pre-training. Then the third component is user data storage. Any user-generated data such as input texts as prediction results are also stored here. This allows for analysis and improvements over time as well as personalized user experience. By separating storage concerns, the database tier ensures that the data is handled securely and efficiently, supporting the needs of both presentation and logic tiers. Integration between these tiers is crucial for seamless operation. The presentation tier communicates with logic tier through RESTful APIs. The logic tier retrieves stored data in the database tier using object relational mapping frameworks or direct database queries. This separation of concerns allows for independent scaling and maintenance of each tier, enhancing the system's robustness and flexibility. My first model is sentiment analysis for suicide detection. Initially, we are importing essential libraries. Pandas and NumPy are used for the data manipulation and analysis. Matplotlib and Seaborn are for plotting and visualization, while NLTK is a library for working with natural language processing and tasks. Then we are going to import our primary dataset containing text data for suicide detection. We also check the shape of the dataset to understand its dimensions. And then we displace the first few rows of the dataset, giving us a glimpse of the data structure and the content. This will provide the detailed information about the dataset, including column names, data types, and non-null counts, helping us understand the dataset's overall structure. Then we clean the dataset by removing rows with null values, ensuring our analysis is not affected by missing data. Then the class distribution. It will show the distribution of different classes within the dataset, giving us an idea of the balance between suicide related and non-suicide related texts. Then we are going to identify the duplicates. We check for duplicates entries in the dataset to ensure the data quality avoid redundant information in our analysis. Then after that, we are going to perform a quick EDA. We categorize age data into predefined ranges and plot the counts of suicide and non-suicide texts within each age range. And this visualization helps us to understand the distribution of suicide risk across different age groups. Then we are importing the secondary dataset that includes different levels of suicide risk detection, expanding our analysis scope. Then we use the transformers model for the sentiment analysis. Here we set up the sentiment analysis pipeline using transformers library. This pipeline will help us to analyze the sentiment of text data, crucial for understanding emotional tones in suicide-related content. Finally, we demonstrate the sentiment analysis pipeline on a sample text. This example illustrates how the model processes text to identify sentiments, providing insights into an emotional state conveyed in this message. Right, so let's move to the second model of my research. So in here I am doing the suicide detection by using the BERT model. So for this model I am using the TensorFlow. So that's why we can see the installation of this TensorFlow, and also I am importing the nested libraries and the dataset as well. Right, in here I am going to perform the data pre-processing part as the initial phase of this model. So my dataset contains two classes, one is suicide and the other one is the non-suicide. I am going to map these two classes with two values. If it is suicide, then I am going to map it with the class number 1, otherwise it will be the class number 0. Right, in here I am going to split my dataset into train and test. As a result of the train dataset, in here we can see some random columns that are there in this train dataset. Then after that I am importing the BERT model in here. Right, so from this point onwards in this demo, I will walk you through the process of building, training and using a BERT model for binary text classification, especially for detecting suicidal comments. We define our model architecture using pre-trained BERT components for text input and processing. The model includes dropout and dense layers to ensure robust classification. The model summary provides an overview of the layers and parameters. Then we check the length of our training dataset to confirm the number of samples available for training. So in here we define the evaluation matrix including accuracy, precision and recall. Compile the model with an Adam optimizer and binary cross entropy loss and train it for 3 epochs. And also we evaluate the model's performance on the test dataset and generate predictions. The predictions are then flattened for further processing. Then we apply the threshold to predicted possibilities to obtain binary class predictions. We then compute the confusion matrix to evaluate classification performance. And then we visualize the confusion matrix using a heat map and print a detailed classification report which includes precision, recall and F1 score matrices. Then finally, we use the trained model to predict the class of new comment. The model's prediction is mapped with a human-readable label indicating whether the comment is classified as suicide or non-suicide. This concludes the code walkthrough. We have covered the data prediction, model building, training, evaluation, and making predictions using our trained BERT model of binary text classification. Right, then let's move to the third model of my research project, which is the multi-class model. So as usual, I am installing Transformers model for this one and I am importing the necessary libraries and also the dataset as well. Right, now this point onwards in this demo, I will walk you through the process of building, training and using BERT model for text classification, especially for predicting the severity level of the text comments. We start by mapping text labels to numerical values for our classification task and verifying the distribution of these levels into our dataset. Then we use the pre-trained BERT tokenizer to convert text data into tokens suitable for input to a BERT model. Here is an example of tokenizing a single text input. Then we prepare our entire dataset by tokenizing each text entry and sorting the input IDs and attention marks, which are crucial for BERT pre-processing. Then we convert our target labels to a one-hot encoded format, making it suitable for training our neural network model. Then we create a TensorFlow dataset pipeline to handle shuffling, batching and mapping, optimizing the training process. Then we split our dataset into training and validation sets, with 80% of the data used for training and 20% for validation. Then we are going to define our model architecture leveraging a pre-trained BERT model and adding custom dense layers for classification. After that, we are going to compile the model with an Adam optimizer and categorical cross entropy loss, then train it for 2 epochs. Right, let's discuss about the prediction part of this multimodal. In this section, we demonstrate saving and loading our trained model using TensorFlow. First, we save the model to a specified directory, ensuring we can reuse it later without retraining. We then load the model back into the memory to verify that the save and load process works correctly. Next, we utilize a pre-trained BERT tokenizer from the BERT base case model. This tokenizer is crucial for converting input text into tokens that our BERT model can understand. We define a function to pre-process the input text. This involves tokenizing the text, truncating or padding it to a maximum length of 256 tokens, and converting it to a tensors with input IDs and attention masks, ensuring the text is in the correct format for BERT model. Another function we define takes the model and process data as inputs, uses the model to predict class for probabilities, and returns the class with the high probability. Right, then finally we prompt the user to enter a comment. This input text is processed and then passed to our prediction function to classify the text. The predicted class level, either level 1, level 2 or level 3, is printed, showcasing our model's ability to accurately categorize new text data. This entire process demonstrates the practical application of saving, loading and using a machine learning model to make predictions on new data. Right, after building these three models, I have built a client application as well. And also that client application has built by using React, and also I have hosted in it AWS as well. So in this EC2 instance, we can see all the data I have hosted of this project. And also this project is a Django project, and in here at the moment this is in running state. Then I will do a small demonstration on how to use this application. So this is my application, and at the moment I am having two comments. So the first comment is a non-suicidal comment and the second comment is a suicidal comment. Right, so let's see what will be the final outcome if I am providing a non-suicidal comment for this application. This application is connected with the hosted Django project, and also that Django project is having the three models, and after going through all three models for a non-suicidal comment, so we are getting this kind of output. So initially we can see the result. If the label is positive, it means this is a non-suicidal comment. So in that case we can't see a sentimental score, and also we can't see a suicide prediction level as well. And finally we can see the suicide prediction, whether this comment is a non-suicide or else a suicide. So since I have entered a non-suicide comment, simply we can see the prediction as non-suicide. Okay, then let me provide a suicidal comment. I'll go back to my notepad and I'll take a copy from the second comment, and I'm going to enter this comment, and let's see what will be the output for this comment. So at the meantime you can go through the comment as well. So this is more like a suicidal comment. So let's see the outcome. So as a result for this particular comment, we are getting the label as negative. So simply it says this is a suicidal comment. So previously we got positive for a non-suicidal comment, and also we are getting the sentiment score as 99.93, and it shows the prediction level or else the severity level of this comment as level 3, and finally we are getting the suicide prediction. So whether this comment is a suicidal or non-suicidal. So for this one it is a suicide comment. Right, now I am back with the presentation to conclude the entire demonstration. So in here I am talking about the evaluation and the future work. After developing the model, it was crucial to evaluate its performance. The evaluation matrix used include accuracy, F1 score, precision and recall. The model showed promising results, achieving high accuracy and positive feedback from the expert reviews. However, there is always room for improvement. Future work includes enhancing the model with more diverse datasets, incorporating multimodal data such as images and videos, and improving the user interface to make the system more accessible. These enhancements will further improve the model's accuracy and usability. To summarize, this research addressed a critical global issue by developing a BERT-based model for early suicide prediction using Facebook data. The model's accuracy and real-time processing capabilities make it a valuable tool for early intervention. Thank you for your attention, and I'm happy to take any questions you may have.